Welcome back to part 2 of the Vex Isn't Scary project. In the previous part, we created the lines that our points will follow. In this part, we are adding the points that move back and forth on those lines. Now, we did some fairly complicated Vex code in the last part. However, one thing that I didn't cover in much depth is the use of sine and cosine. In this part, we're going to need to use sine and cosine a bit more, so I'm going to explain it a bit better. Honestly, it is just a useful bit of maths to understand, so here we go. Right, so here we have a sine and cosine graph. And now you're probably getting flashbacks to high school and all the horrors of trigonometry, but don't worry, I'm going to try and keep this as simple as possible. I also struggled in high school with maths, so this is from the perspective of somebody who really didn't understand maths, who had to learn it after high school. So this is kind of just what I've learned about sine and cosine. I'm going to explain it in the most simple way that I understand it. As you can see here, we have these two graphs, sine and cosine. Now, when you feed a certain degree value into here, and this could be converted to radians and it would look the same. So 90 degrees, right, returns a certain value when fed into a sine function. And in the cosine function, it returns a different value. So as you can see, if we feed in 90 into a sine function, it returns a value of 1. If we feed 90 into a cosine function, it returns this value of 0. So why is that useful? Well, the thing is, if we put this to x and y, so if we say our x position of a particular point is equal to sine of some degree, so the degree would be theta, that's what we would call it, and maybe y is equal to cosine, and you can do this the other way around. It can't be y equals sine and x equals cosine. I believe that's actually mathematically correct. I'm not sure, don't quote me on anything that I'm saying here, but this is my understanding of it. When you have x equals sine of a particular degree, then the x value is equal to whatever's returned here. So if we're thinking of a circle, and we know that a circle has 360 degrees to it. So if we have this circle, and let's just divide it up, just so that it's easier to understand. So if this is, say, 0, and this is 90, this is 180, this is 270, and, it repeats. When you reach 360, it will be the same as 0. So this is 360 or 0, and you can see on our sine and cosine, when it reaches 360, the graph resets, right? It starts at the same place. So any value past 360 is just a repeat. It just repeats the function. So if we feed 360 into these two functions, we'll see that x equals sine of 360, y equals cosine of 360, and then we can just look at the two graphs and figure out what the values are. So x would equal, and we just look at what 360 is, 0. Y would equal, and we just look over here, y would equal 1. And that's exactly what we have if this is our Cartesian plane. So in Houdini, this would be your y-axis, this would be your x-axis. Now we know that this is 0, 1, 0, right? And we know it's 0 because this is flat, it's 2D, there's no z value. So it's 0, 1, 0. And then we can feed in 90 degrees and figure the same thing out. So if we feed in 90, then we just have to take a look. So then we see that at 90, that sine of 90 is equal to 1. So we know that x equals 1, y equals 0. And that's exactly what we have over here. We have x equals 1, y equals 0, z equals 0. So you can feed in any value on the circle and figure out the corresponding value on your sine and cosine graph. And so this is actually something that you can recreate in Houdini, which is kind of cool to do. So in Houdini, let's do that. And we're going to do it as a separate thing. I just want to show you how sine and cosine work. So over here on the side, we'll make a new attribute wrangle, bring up our string editor, and I'm just going to kind of speed through this just to show you what's happening here. So we'll create some points. In points equals chi points float x and y equals 0. And this is something you'll actually do often. And so we'll also do pos, and we'll do for int I equals 0, I less than the number of points that we have, increase I, so I++. In here, what would we like to do? So we're going to create a sine and cosine graph. So we say x equals I, and let's just shorten our graph, so 0.01. So this just means that every point is going to be placed on the x-axis, and then their y value will be equal to a curve. So sine of radians of I. And then we can just say pos equals set x comma y comma 0, and then we can add point. And I'm actually going to assign this to an integer variable. So I'm going to say int sign pt equals add point 0 comma pos. And then if you apply and accept, and then add some points after creating your spare parameters. Oh, and of course this won't work unless we change this to detail. We don't have any points to run over. So now if we add some points, it will create a sine curve, and you can just refocus on it with G and F. So if we set this to 360, you'll see a full sine curve. And what I'm going to do is do the same and create a cosine curve. So just Control C, Control V, paste this over here, and we'll just change this to cosine. And change the name of this over here to cos PT. And now we have the two like that. And this is actually something pretty cool that you can do. I'm going to bring this back up. You can actually set a point attribute. So set point attrib. And you can see that it takes a couple of things. It takes a geo handle, a string name, the point number, and a value. So what this is doing is it's assigning a value to an attribute. So we need firstly the geo handle, the name of the attribute. We're going to do CD. We want to change the color. We're going to say change the color of sign PT, and let's make it red. So 1, 0, 0, close brackets, just like that. We're also going to do set point attrib for the other point, 0, the attribute to change, the point to change it for, and the value to give it, 0, 1. Semicolon at the end, apply and accept. We now have a blue and a red one. Cool. And then finally, I'm going to show you how this relates to a circle. So if we take everything that we've done here and do one more of these, then we can actually say that x equals sine of radians I. And if we just remove the assignment of the variable, we can do that over there, and we can move our circle over that way by subtracting from our x position. So let's just do that. And so now you can see the relationship between these. And so you can actually recreate this code and play around with it. And this sort of code will kind of help you understand sine and cosine, because you can see now that they relate to the circle. If we set x to the sine of our degrees and y to the cosine of those same degrees, we end up with a perfect circle. And this is maybe even a better explanation, because here you can clearly see the values. So if you put in 90, you can see what the values are, 180, and you can also see that it's making a semicircle. 270, 360. So now that we have that out of the way, let's continue with making points that move along these lines. So press Alt plus E to bring back your string editor, and we're just going to do a few things in here. Firstly, we're going to add a comment. So do a double /, and we'll just call this top part line generation. And under all of that, we'll create another comment, and we'll call this one point generation. So now we know that all of this code is line generation stuff, and everything that we're going to be doing now is point generation stuff. So to help you understand this, let's just put this into perspective. So we know we have all of these lines, and each one of them has a start point and an end point. Each of these points are positioned at sine and cosine of theta, right? So this is sine and cosine of theta over here, and over here, where theta is different for each one of these. So when I is equal to 0, theta is one value. When I is equal to 1, theta is a different value. When I is equal to 2, it is a different value. And this is the same as saying theta times 1. When we find our opposite values, we do -1 times theta, which is the same as negative theta. So we're doing negative theta on all of these, and that's what we feed into our sine and cosine, right? So we know that if this is 1 over here, and this is -1 over here, then anything in between is a direct interpolation between the two. So if we have 1 over here and -1 down here, then everything in between we can figure out. So we know then that the middle point is 0. We know that halfway between would be 0.5. We know that halfway between here and here would be -0.5, And so how does it help us knowing that this is just a range between 1 and -1? Well, if we look at a cosine graph, we know that it goes from 1 to -1. And that's exactly what this does over here. So it makes sense that when we want to calculate how our points move up and down these lines, that we would use cosine. So to calculate that, what we're going to do is we're going to do something similar to when we calculated our theta value. Remember, we said 180 divided by lines times I was our theta value. We just converted it to radians. But if we don't convert it to radians, we end up with values like 0 and 90. Then if we treat time as degrees, we have something very interesting on our hands. Because if we have frames that go from 0 to 360, so if these are our frames, so what we'll do is we'll take the current frame, and from that we'll subtract these values. So say frame is equal to 0, then we'll say 0 minus 0, 0 minus 0 is 0, and on cosine that gives us a value of 1. And we established that a value of 1 means that we're at the start point of our line. So we're over here. But we have 2 lines. So we also have to do that calculation for the line over here, for this horizontal line. So we go 0 minus 90, and that gives us minus 90. And minus 90 on cosine is actually the same as 90. So that returns a value of 0. That means our other point would be there. And so that works at every frame. If we have a frame of, let's say, 45, we'll have 45 minus 0, 45 minus 90. And the 2 values that we'll get are 45 and 45. So we'd have a point there and there, which are both at 0.5, so to be there and there. And so, as you can see, as time would increase, these values over here will slide around back and forth. And don't worry about the maths too much, but I really want to throw you into the deep end with this code so that when we get out onto the other side, you'll see that most of the time the code that you're using is actually quite simple. I'm showing you about as advanced as it gets. Now that we have this concept going, let's actually implement it in code. So the first thing we're going to do is actually create something similar to float theta. We're going to create a float and we're going to call this one position. We're going to make it equal to 180.0. Remember, we want this to be a float. We don't want to be dividing by 180 and only getting an integer. Divided by lines, multiplied by I. So it's the same thing as our theta, except we're not converting this one to radians just yet because we need to do some more things to it. So the other thing that we're going to create is something called float progress. And this is going to be equal to our frame minus this position value that we just created. So the idea for this is for the current line that we have created, we want to see where along our semicircle this line is. And so once again, we're finding the distance between the points in degrees. So if we have 3 lines and this is the second line, it'll be 180 divided by 3, which will give us 60, times 2, which will give us 120. So it'll be 120 degrees. Then what we're going to do is we're going to say, take the current frame that we're on and subtract this from that frame number. Okay, so now we're going to use this same progress value, and we're going to say that progress is equal to the cosine of our progress in radians. And this is going to give us a value which ranges between 1 and -1. So what we're going to do is we're going to find a new position. So now we want our x and y. So once again, we can just reuse our old x and y values. So we can say x equals, and we're going to do sine of theta. So this is exactly what we've done before. We're also going to do y equals cosine of theta. Now this looks familiar, I'm sure, because this is exactly what we did up here, right? Where we said x equals sine of theta, y equals cosine of theta. And if you remember correctly, this little bit over here, where we do these calculations, finds these 3 points for us, right? It finds these 3 points. And if I just comment out our add prim stuff, it's these 3, right? So these 3 points, when they are multiplied by -1, they get flipped to the other side. Now, that's actually very close to what we want our points that are moving to do. We want them to go from there to there and back and forth, right? We want them to move back and forth between these positions. So that means that we want to multiply them by a value that changes from 1 to -1, and then back to 1. And that's exactly what this code over here does. It gives us a value between 1 and -1. Remember, cosine goes from 1 to -1 based on degrees. So all we have to do over here is multiply this by progress. And over here, once again, by progress. And then we can actually just create another vector. So maybe we create one at the top here. We just put a comma and we say line PT. Right, so we have the line start, the line end, and the line's point, the one that moves. And then we can just use line PT over here and say line PT equals set x, y, 0. And then all we have to do is add a point. Add point 0, line PT, semicolon. Apply and accept, and we have 3 points. And if we move along our timeline, they move in simple harmonic motion. And so we can actually change our frame range to 360. And as we move along here, you'll see that we have this where it moves along the lines. And if we reduce this to just one line, you can see that it just bounces back and forth, right? If we have 2 lines, they bounce back and forth. And as you increase this, you begin to see that effect of the circle. And each and every one of these points are moving on a straight line. So just to revise what we did in this tutorial, we found the position for each line. So this, unlike over here, we're just finding the degrees. So it's the degree for each starting point. So it would be 0, 45, 90, 135, and so on. And so by finding those starting positions for each line, what we can do is we can minus the frame from that. And that's actually just part of an equation. So when we find the frame minus that position, we put it into progress, and then we can feed our progress into a cosine graph. When we feed it into that cosine graph, we get a value between 1 and -1, depending on how far along our timeline we are. And then what we do is we multiply that value by our sine of theta and our cosine of theta to find x and y respectively. We then feed x and y into line PT, which as before is just a vector. So we're making a vector to find the line PT position. We're then adding a point at that position. And the result of that is, of course, this optical illusion. Now, if you understood this, I just want to say well done, because really this is not basic coding. This is quite advanced, and even people that have worked in Vex for a while might not be able to get this immediately. This took me a couple of days to come up with, to figure out, and it does use sine and cosine, which does add to the difficulty. Now, in the next part, what we're going to be doing is we're going to be expanding on this code, right? We're going to be turning this into an actual effect that we can render out rather than just what we have here. So we're going to be adding very short pieces of useful code. So the next